So, I want to do one last thing which I am very fond of, and this is to show you that Bayes nets encompasses satisfiability, 3 SAT. That is pretty awesome. If you actually think about it, you can come up with this reduction, but in the spirit of making it quick, I will show you the result. So, let us say I give you a CNF formula u or not v or w and not u or not w or y. Let us say I want to create a Bayes net which solves the SAT problem. So, what is the SAT problem? To figure out if the formula is satisfiable or not. Can we create a Bayes net and do inference over Bayes net so that the answer to the Bayes net solution gives me the answer to the satisfiability problem. So, how do you do it? You take each logic variable and make a random variable out of it. So, u, v, w and y, they are all random variables, and you give them a prior probability of 0.5 to be true and 0.5 to be false. Okay. Then you take each clause and create a OR node here. So, one OR node would be u or not v or w, one OR node would be not u or not w or y. This also needs a conditional probability table. So, your conditional probability table will be 0 if u is false, v is true and w is false, and 1 otherwise. So, it is basically saying you are representing the OR function in the conditional probability table. Right. And then you have an AND function here which basically says that this is an AND function. So, if all of them are 1, I am 1, if any of them are 0, then I am 0. So, now what have we done? We have given a conditional probability table for each node in my Bayes net, and I have also given the prior probabilities for each of the initial random variables. Now, I do Bayesian network inference. What is the inference I do? I say what is the probability of AND. Now, think about what does that give you. If probability of AND is 0, what does that tell me? When would probability of AND be 0? If the formula is unsatisfied. There is just no way to make probability the AND node 1. If probability of AND is 1, what does that tell me? All configurations make AND true. That is not going to happen in general. But usually it may be a number between 0 and 1. So, what does that number represent? And this is very interesting, because all the original variables are independent, you will have all possible configurations captured in this. And if there is only one solution to the whole problem, probability of the AND will come out to be 1 by 2 to the power n. If there are exactly 2 solutions, probability of AND is going to come out to be 2 over 2 to the power n, and so on and so forth. So, what is very interesting is not only is Bayes net telling you if SAT formula is satisfiable or not, it can do something bigger. It can count the number of solutions of the SAT formula. So, if we can do Bayesian network inference, not only can we do SAT, we can also figure out how many solutions that particular SAT formula has, and that particular problem is, by the way, called model counting. So, SAT is an NP complete problem, but if you are looking at the model counting problem, that is what is called the sharp P complete. Sharp P means counting the number of solutions of the NP complete problem. So, Bayes net, unless all this hierarchy collapses, it is in a more advanced complexity class than NP complete problems, than NP. It is sharp P. So, Bayes net always has more information than SAT. Okay, so that is the first thing. So, exact inference has to be NP hard, right? There is none, you can't get away from exponential. Second, we like in CSPs, if it was a tree, we could do it in polynomial time. There is something called a polytree structure, where if it is a polytree or a tree structured Bayesian network, then you can do inference in polynomial time. Like you have cycle cut sets in CSPs, you have probabilistic cut sets in Bayesian networks. You have tricks of looking at the structure and doing things with that, we have equivalent tricks here. We have variable elimination here, we have bucket elimination there. You can do your full deep analysis of just comparing CSPs and Bayes nets, and you will find that there are so many similarities that it is not even funny. They are just two sides of the same coin, though they are in slightly different complexity classes. And the next thing we are going to do after today's lecture, in the next lecture, is that we will talk about an approximate inference algorithm, which is better than well, it's sort of constant time in some ways. Constant time, because if you spend more time, you get a better approximation. Okay. So, that is what we will do in the next class. It uses the general principle of sampling, and we can stop here. Thank you.